My next guest is Ray Upton, Vice President General Manager of Connected MCUs from TI.
Thank you.
TI introduced a new technology this morning. It's called BAW technology, bulk acoustic wave technology. What are the big advantages of this technology?
Yeah. So we introduced a technology today called bulk acoustic wave. It's actually not a new technology.
No.
It's a technology that's existed for some time. Bulk acoustic wave and surface acoustic wave, of course. What we've done, though, is we've integrated this bulk acoustic wave technology into a standard semiconductor process, and now we're integrating that technology into other devices. So what we introduced were actually 2 new devices utilizing this bulk acoustic wave technology.
But it's not integrated into the wafer, it's on top.
Correct. We build the bulk acoustic wave IP on a wafer, but we integrate it into the package. So you have your first device that is the base die, and then we integrate that bulk acoustic wave into the package as part of that overall system.
And what is the big quartz crystals? You have thousands of
everywhere.
them.
They're everywhere.
What is the big advantage of integrating bulk acoustic wave technology inside of the packaging?
So the interesting thing about crystals, we've talked a lot about big data for the past several years. Big data and all of the new applications that are developing as you can start to draw information from sensors. Everything from the sensor to the cloud, and you're starting to think about how do you now utilize this big data to make informed decisions. Well, this requires a capability in clocking that's beyond what a typical quartz crystal will allow. So what we've done here and what's unique about this is we've introduced 2 different devices. The first one is a connected MCU, a wireless connected MCU that requires no crystal. The second device that we've introduced is a network synchronizer on the clocking side. And the advantage of these products really are bulk acoustic wave is immune to many environmental concerns. So whether that's temperature, various different ranges of heat, certainly shock and vibration, aging over time.
Is it immune or can you compensate it easier?
It is, so what we've done with the device is we actively compensate over both temperature and power for the life of the device. So since it's a semiconductor technology, you don't have the aging capability, but regardless we actively compensate over time, and then you have the inherent immunity to shock and vibration. Not to mention we can increase the performance of the clock.
In comparison to, let's say, high-end quartz crystals?
That's absolutely right. So, for example, in our connected MCU, so the crystalless wireless MCU that we introduced today, the CC2652, in this device, we've got full operating performance at plus or minus 40 ppm over the entire operating range of the device over life.
Okay.
All right. Now, in the clocking device that we introduced, the network synchronizer, we're pushing performance. We're talking about 50 femtosecond jitter performance. So you're talking about being able to push from 1 gigabit per second up to 400 gigabits per second in the clock capability at this point. So it's moving your ability to move this big data in very, very, very high rates, much more so than was previously capable.
In which other applications do you see benefit if you use BAW technology?
So we think about this. We've taken the liberty of imagining a few of these applications on the front as we get these 2 devices into the market. Obviously, on the telecommunications side, you want to have that big pipe of information, be able to expand that big pipe of data flow. And that's really where the network synchronizer comes in. So this now is enabling a very different rate of performance.
Yeah.
On the smaller end, out at the sensor side, you can think about, if you think about building automation and factory automation applications, for example, the simplest example that I use is perhaps you want to have a sensor in a motor.
Does it mean that you integrate this technology, for example, in sensors too?
Not in the sensor.
Okay, but in the microcontroller.
But in this is a wireless microcontroller.
Yeah, okay.
So the CC2652 that we announced today that includes the ball technology, this is a product that's available in the market now without the ball.
Yeah.
So it's already a highly integrated wireless MCU. So it includes a microcontroller core, it includes a full RF core, it includes lots of analog peripherals, a sensor subsystem that allows you to take these sensor inputs, and of course all of your memory that's required there. What we've now done is integrated the ball technology, so we effectively bring all of the clocking inside the device.
I would guess it's probably a little bit more expensive for you to produce the MCU, the clockless MCU, but for the client probably it's an advantage because they reduce their BOMs on it.
Correct. They're going to reduce their bill of materials because you have less external components to deal with. You're also going to drastically decrease the complexity of the design. You don't have to now worry about trace lengths and all of these kind of stuff on the circuit board that has an inherent reaction with the actual wireless itself. You've got the potential now for a much, much simpler design. So what we've got is there's no change to the actual microcontroller cost. Of course, the resonator device has a cost associated. But actually, we think the trade-off is quite nice when you look at all of the benefits. It's not just integration, you're actually increasing performance.
Do you have some other product groups? TI has a huge product portfolio where you can use this BAW technology?
Yeah, well, we chose these first two devices because we think, first of all, it demonstrates exactly how powerful the technology is.
Yeah.
Right? So to be able to say that we've got the first crystalless wireless MCU, that's a proud statement for all of us. On the clocking side, to say that we can increase the performance by 25 dBm at that phase noise versus frequency offset, that is a huge increase. So we chose these first two devices because we think it really demonstrates the technology. Yeah. Now, in terms of your question and what comes next, we'll have to wait and see. All right? I have a very large portfolio of sub 1 gigahertz to 2.4 gigahertz up through Wi-Fi type products in my portfolio, including wired devices. So the nice thing is we think it has a very broad applicability, and we can do lots of different things with the technology.
Okay, Ray, thank you very much.
You're very welcome.